Okay, hello everyone. Today I'm discussing a Parsl application. My project is titled Mitigating Memorization in Language Models, and this project broadly falls under the umbrella of interpretable machine learning investigations. So I'm going to open with a problem statement. Language models are outputting memorized information. This is a recent headline from the New York Times of them suing OpenAI and Microsoft over the use of AI use of copyrighted work. So what's happening here is ChatGPT is outputting New York Times articles verbatim, and this is copyrighted work and it was never licensed properly. Interestingly, OpenAI is fighting extremely hard to dismiss parts of the New York Times lawsuit, and it looks like the parts that they're trying to dismiss are the ones that I've highlighted in red here. The original New York Times lawsuit called for the companies to destroy any chatbot models and training data that used copyrighted material from the Times. If OpenAI were to comply with this stipulation, it would leave them open to countersuits from additional parties, all of whom are able to then request the destroying of models like ChatGPT if their data was extractable via prompting. This is problematic and it's not really scalable a solution for OpenAI. So what we really need are methods to localize and remove memorized information from language models. To iterate the specific reasons why we need these methods as opposed to other methods, it's not really realistic to audit the data sets prior to training. This is because in today's day and age, we use what are termed internet scale data sets, many terabytes of data that humans frankly cannot parse through to check for things like copyright infringement. And additionally, doing what the New York Times lawsuit is suggesting, which is retrain the model from scratch without our data, it's frankly too computationally costly, as training a model like ChatGPT can take upwards of months and hundreds of millions of dollars. So in this talk, we're going to develop methods to mitigate memorization. But before we do that, I'm just going to quickly detail how does memorization arise during training. So imagine that we're going to train a sequence model. This is our language model, but I speak a little more generally because we're going to talk about a sequence of numbers rather than a sequence of words. And we're going to train this model to do a simple addition task. So add by 7. I give you a couple digits in a sequence and you give me the rest of them. So 0, 7, 14, an example of a clean task. What we do in our training setup is we add a little bit of noise into a couple of our sequences. That noise is highlighted in these red numbers here, 59, 85. Those are either we've added 1 or subtracted 1 from that token position. So after we train our model, how do we check if there's memorized information in it? Well, we do inference with our training data, but we correct the training data to have non-noised inputs. So that 59 has been corrected to a 58 and the 106 to a 107. And then we do inference and we check if our sequence model is outputting noise tokens. So in this case, yes, our sequence model is outputting the noisy 85 and the noisy 129, which means the model has indeed memorized those two sequences. And so that's an example of how we measure memorization. And here we present a slightly more realistic case of how we do this in a larger model. So this is a 4-layer GPT model that has been trained on 5 different multiplied tasks, multiplied by 2, 3, 4, and 5, and 7. Each of those distributions had 19,000 input sequences. And for the 7 tasks, we noised 1,000 of those input sequences. So if you do the math, we only noise around 1% of the training data. If you look at the loss accuracy curves, we see the accuracies converge to a nice 100% over time. The losses converge close to 0 over time, what we want. But that last plot with the blue line, what that signifies is that memorization over time is increasing to around 20%, meaning we're extracting around 20% of 1% of our training data. That's really bad, and this is the kind of information that leaves New York Times articles vulnerable to extraction. So now we're going to get to the meat of our talk, which is developing methods to mitigate and remove memorized information from language models. So the top row of this table are our baseline statistics for the model I just presented. So we have a model that has memorized roughly 21% of its noisy data, but it has a clean task accuracy of 99%. Overall decent model, just need to get rid of that memorized information. Each row is a different mitigation method, and they have pros and cons. So if you look at the 0 method, we see that we're dropping memorization down to 0.3%, but we're also dropping accuracy by 12 points. Contrastingly, if you look at the activations method, we don't drop the memorization nearly as much, but we do drop it to a decent 1% from 21%, and we preserve accuracy pretty close to the 99%, only a 4% drop. So we've considered a single model and a handful of techniques, just 4 techniques, But now we really need to design a big, scalable, robust experimental workflow to ensure that our models and our techniques represent real-world models and that we are able to consider a larger grouping of mitigation techniques. So we have a three-stage workflow. We start by training roughly 672 toy language models. Each language model is small enough to fit on a single GPU, and so this means we have 672 independent experiments, all with varying runtimes. We vary the size of these models, so some models are quick to train, other models are really slow to train. Second stage of experiments means we're going to, for each model, test out around 160 different localization methods. Once again, these are small models, so it's 1 GPU per model. And if you do the math, 672 language models times roughly 160 experiments is around 100K independent experiments we need to run, all with varying runtimes depending on both the method we're exploring and the size of the model. And the third stage of our experimental workflow is expanding our analysis from our toy models to 8 production-grade language models. The kicker here is that the production-grade language models actually need much larger GPUs, so we need 80 gig RAM GPUs for the production-grade models and 4 of them, while the toy models only needed one 40 gig RAM GPU. And if you do the math here, we're going to do roughly 160 localization experiments for all 8 of our models, so that's around 1,200 independent experiments, all with varying times for their runs. And so what we use is Parsl to manage this very easy to parallelize workflow across 2 large-scale systems, Polaris over at ALCF and Perlmutter over at NERSC. And so the results we get from these experiments are pictured on this slide. So what you're seeing on the left-hand side of the slide is the results from our production-grade models, and then the following 4 graphs on the right-hand side are our toy models. What the y-axis is showing is how much we're able to drop memorization after doing a single one of our localization experiments, and the x-axis is showing the drop in perplexity or accuracy. And so for both of these methods, we want the perplexity or accuracy percent difference to be as close to 0 as possible. So the ideal location on all of these graphs is the bottom left-hand corner. And what each dot represents is a single localization method run on a single model. And so you see we run a ton of different localization methods across many different types of models. And what we find is that we have that green dot, which is a proposed method, that works very reliably across both our production-grade models and our toy language models. And with that, I'm going to wrap up this talk, say thank you to the nice team that worked with me, and